Okay, we need to continue. In this part, we are going to have a look how the NCCL communication library works. Okay, what's under the hood? How does it work? This is the thing we want to find out. Okay, to make things clear is that maybe we just need to compare this NCCL communication library with the MPI library. We know that MPI library, if from the programmer's point of view, is pretty much the same as NCCL, because for MPI library at the beginning, what you need to do is that you call this MPI initiate functional call to build up this MPI communication structure, and then you do your communication. And then at the end, you need to call this MPI finalization, means you need to destroy the communication structure. These are the three main steps for MPI communication. But we need to bear in mind that for MPI communication, the first step is going to be much more simpler than the NCCL in the NCCL communication library. Why I'm saying this way is that, there is one important fact for our discussion is that if you have to deliver a system to the customer, a high-performance computing system by using MPI to do the communications, there is the interconnection network. Usually, the biggest market share for the moment is the InfiniBand network. Now, if you have to deliver a system with InfiniBand network to the customer, after the system has been delivered, you should have built up a network to carry this kind of MPI communication, and your network should be with a kind of topology. And then is the vendor's responsibility to deploy the routing algorithm for the physical interconnection network you have delivered to the customer. The most popular right now, the most popular communication network, InfiniBand network, it seems is Fed tree, and after you have built up this kind of Fed tree topology, when you have to deliver the system, you have to deploy the routing. And then that means at the end, after the system has been delivered, all the nodes of the system, all the nodes, what they need to do when they have to communicate to each other is that they just need to put data into the network. And the network knows if you want to send your data from node A to B, if you put the data into the network by using the routing algorithm, they know how to deliver the data finally to node B, because there is already this routing algorithm built up for this InfiniBand, for this high speed interconnect. For our age, for this moment, that's pretty much the InfiniBand network. But this is not the case for NCCL communication library. For NCCL communication library is very similar to MPI library, because you still need to have three steps to carry out your communication. The first one is the same as MPI, is called NCCL. Initialization, something like this one. What's that? It's the same thing. You need to build up this communication structure, and then the second step is that you do your communication, which is the same as the MPI library. And then at the end, there should be another one, which is called NCCL finalization, something like this. You need to destroy the communication structure you have built up. But there is a very big, a very important difference is that if your network for MPI you have delivered to the customer the InfiniBand network, then after the network has been delivered, the routing should has been set up. So this is for MPI libraries for MPI communication. But for NICO communication, the fact is that you have delivered the system to the customer. Okay, if you have InfiniBand as the network, network between the computing nodes. Okay, the network, the network, the InfiniBand network for this stage, for the first stage, the InfiniBand network should has been delivered with a routing already set up. Okay, so that's the same as the MPI communication library. But the fact is that for NICO communication, you need to go through three kinds of networks. InfiniBand, which is one of them, you need to also go through PCIe, and you pretty much also need to go through NVLink. Okay, so three different kind of networks with different kind of technologies. And then only one has been delivered with the routing, which is the InfiniBand one. The InfiniBand network has been delivered with routing, but not the other two. So you don't have the routing with the other two kinds of networks. That means for NICO communication, the first step is that the NICO communication initialization part, you have much more work to do, because to build up this communication structure, the communication infrastructure, you just have one part of the network, which is the InfiniBand. The routing has been set up. The other two parts of the whole network, there is no routing set up yet, or there is no global routing for this NICO communication library. That means for GPU, when it has to send a data to another GPU in this network, it cannot just put data into the network and the data will be delivered to the destination by the network. The network, the whole network, it combines three kinds of technologies, three kinds of links or switches, and then you have just one of them with the routing, the others without. So the message cannot be delivered like we can expect for MPI communication, is that you put data into the network in the memory of the communication network adapter, and then you tell the network where is the destination and the data will be delivered. That's going to happen with MPI, but it cannot happen with NICO, simply because the NICO you are going is the communication network is made up of three kind of networks and three kind of technologies. There is no ready to use routing between the GPUs. That means for NICO library to work properly, we have more things to do for the NICO communication is initial part. So for this first part, that's to build up this communication infrastructure. There are three kind of things that the NICO library has to deal with. A, it has to do the topology detection, and B, it has to do graph search. C, it has to do the graph connect. And then the communication infrastructure for GPUs, we can claim that it has been set up. Right now, you can go the next step, do your communication by using CUDA kernels. And then at the end of your communication, you don't need this communication infrastructure anymore. You can call NCCL finalize to destroy this communication structure. So here, this is the difference between the MPI communication library and the NCCL communication library. Now, another point is that with traditional MPI communication library, if you have a system with 10,000 nodes, if you have a job, you just need to use 1,000 nodes. You just take 1,000 nodes. You use part of the communication network, and still because the routing has been set up for the whole network. Now you are just using part of the network. It just works for you. But here is that each time you launch your job, maybe you are using 1,000 nodes, and each node with 8 GPUs, and the next time you want to use 5,000 nodes, each node with 1,000 with 8 GPUs. So for these different scenarios, you are demanding different quantity of nodes. Each node may be with the same quantity of the GPUs, but then because your quantity of nodes is different, or your quantity of GPUs per node could be different. In that case, you have to set up for these two scenarios, two different communication schemes for your application. So that means the routing for the NCCL communication library is one-off. You launch your job, you set up your communication infrastructure, you do your job, you do your communication, and then you destroy that. But for the second time, you need to launch again even the same quantity of nodes, the same part of nodes that you have used. If you launch the second time, the same work, the same job, you still to redo this kind of routing, because this is one-off routing for NCCL communication libraries. But for MPI communication library, the routing has been done when the system has been delivered. If you have no trouble throughout the lifetime of the system, you don't need to do that again. So each time you just ask the system to give you the quantity of the nodes you need, and then you can just carry out your communication, and you don't need to worry about the routing because that has been done. But for NCCL communication libraries, that is kind of one-off routing setup, and each time you launch the job, you need to do this kind of routing. This is a picture I have pulled from the internet. It's called a NCCL architecture. I think the architecture is not the best word to explain this picture. This picture should be called the NCCL setup steps. Okay, so to set up the NCCL communication infrastructure, you need to go through A and B and C, which equals to the NCCL communication initialization, and then you do your communication, and then you destroy your communication infrastructure because you don't need that anymore. Okay, so we are going to have a look of this NCCL communication infrastructure setup steps one by one. Okay. The first, the topology. The topology here doesn't mean the global network topology. It means per node topology. Now, here the first thing that the NCCL library need to deal with is the topology detection. That means the NCCL library, at the beginning, you call this NCCL You call this NICO initialize functional call, and then the NICO will start to do the topology detection on all the nodes you want to use to run your job. So for each node, the NICO library need to have a look of the CPU architecture and the vendor specific informations that could be located in the system, and the NICO need to check all this information, and then the NICO library, part of its job is to do to find out the per node PCI topology, speed and CPU affinity. That's something the NICO library need to find out at the very beginning for each node. And then whether you have the NVLink or not, what's the setup of the NVLink? This is something also the NICO library need to find out. And then the InfiniBand network, multi-ports, how many ports, socket direct, etc., and IB verbs. All this information, the NICO library need to detect when you are going to call this functional call in your code, and then some further information will be collected from cloud hypervisor, etc. And then all this information could be stored in the XML format, and it's called raw XML topology. And this kind of information could be dumped into a file. Okay, so you have got the information, and then what it needs to do is that it needs to build up this graph. The next step after the detection has been done, the next the next step is going to do the graph search. Okay, the information has been collected. You need to the NICO library need to build up this topology, because here is topology detection. You collect all the information you need to. You got all this information. You know the per node topology, and then you need to build up a graph for this topology. And here we can see the examples that the NICO communication library that could build up for different kind of nodes. And the first one is the traditional dual socket x86 nodes, and with PCIe adapters, GPU in the form factor of PCIe adapters. The GPU are connected to the CPU by using the PCIe link. We have 4 GPUs for this CPU, and another 4 GPUs connected to this CPU, and then you have one NIC connected to the PCI switch. This is the topology that the NICO has found out for the kind of nodes we discussed in our section 3. And then the DGX1 and the DGX2 are the servers, the GPU servers with GPUs we discussed in the current section 4. That's the GPUs in the form factor of SXM module from Nvidia, or the OAM module from AMD. So the library needs to build up the topology graph for each node. For DGX1 node, okay, for example, you have 8 GPUs, and you have two GPUs sharing one PCIe switch, and you have a NIC shared by the two GPUs. And this is the topology built up by the NIC library. And then we have, furthermore, we have these DGX2 systems. You have this here we have 16 GPUs, and these 16 GPUs has been connected by the NVLink switch. And then two GPUs are sharing one PCI switch, and the switch is also connected by a NIC. Well, supposedly it's the InfiniBand NIC. Okay, this is the most common case for the moment. Okay, and then the NIC library is going to build up this kind of topology. And then there is also this DGX A100 system. The NIC is going to build up a topology graph for each node that is going to be involved in your computation. Okay, so first step, no, the step A for the first part of the NIC communication initialization part, the step A, and then the NIC library it needs to do a per node graph search. Well, because here is that you have this kind of per node graph, and then the communication is that you have only one NIC. If you have to communicate with, if the GPUs of this node have to communicate with other nodes, connect to the other servers, it has to go through this NIC. There's no choice. And then between the GPUs, you can go through this. This is a PCI link. You can go through this PCI link, or you can go through this CPU, and this is x86 CPU, and you go through this x86 CPU. You are going to reach to the other part and reach the other GPUs, and finally you are going to do a ring. Okay, we are going to have a look maybe a little bit in detail of this this graph, this node graph. This node graph, for this node graph, okay, we have 4 NICs and we have 8 GPUs. Okay, now here, if we think about this NIC, there is one way to reach each GPU from this NIC is to do a ring. And the ring is that you get into this NIC, you get into the GPU 1, and then this is PCIe link. Right now it's PCIe link. And then you can go through this is NVLink between GPU 1 and GPU 2. You go NVLink. And from GPU 2 to GPU 6, you go NVLink. This is NVLink. And then you go NVLink again. All these are NVLink between these GPUs. All these are NVLink. So, and then get off this GPU 0, you are going to pass PCIe. Okay, PCIe in, PCIe out. Between these GPUs, always NVLink. Always NVLink. This is the way to pass through each GPUs from one NIC adapter. Okay, now the fact is that we have for NVLink we have quite a lot of bandwidth, and the PCIe is much more slower than NVLink. So, but here you have between GPUs, between intranode GPUs, you have enough bandwidth. There's no problem. But the fact is that if you want to reach to GPUs connected to other nodes, you have to go through this low-speed NVLink, PCIe link, going through this PCIe switch and the NIC, and you pass the NIC. The NIC could be InfiniBand network, and then later after you have get out of this from this NIC, you are going to go through the InfiniBand network. Okay, that's one possibility. Now, the fact is that you have quite a lot of bandwidth between the GPUs, but you have a bottleneck. The bottleneck here is the PCIe. Okay. To handle this kind of situation, what Nvidia has done is that they build up multiple rings. Multiple rings. We can consider this one is a ring. You get in, you pass all the GPUs, and you get out from the same NIC. If we think the NIC as the starting point and the end point, this is the ring. Okay. To remove the bottleneck, what Nvidia has done is that their NIC library can build up multiple rings. The second one may be you come in from this PCIe link, and then you pass through all these GPUs, maybe like this. You pass through all these GPUs, and then you come back and you get out from here. So you have multiple rings. If you think this NIC is the starting point and the end point, that means you are going to have 1, 2, 3, 4 rings for this 8 GPU. That means you need to sum up the bandwidth of the 4 NICs to compensate for its low speed, the low bandwidth of the PCIe link. Okay, so if we look at this DGX2 system, DGX A100 system, pretty much Nvidia NVLink is using pretty much the same technology, the same method to build up the communication rings for each NIC adapter. Here for this NIC adapter, you have a ring goes through this NVLink switch system. It passes all the GPUs and get out from same adapter. And then the same thing for the second adapter, the third, the fourth. You have 8 adapters. You have 8 communication rings. And then the GPUs of this node, they are going to, the total bandwidth for the GPUs to communicate with GPUs connected to the other nodes. For the inter-node communications, the bandwidth you can have is 8 times the PCIe link bandwidth. You have the PCIe link here, and you have the PCIe bands because you have 8 PCIe adapters. This is a way for Nvidia to increase the bandwidth, inter-node bandwidth. That's by using multiple GPUs at the same time, and you are going to have the aggregated bandwidth, which is 8 times of a single PCIe. Okay, so DGX follows the same idea. So here is that for this DGX, this is the example is showing only one ring. Okay, so here for the per node graph search, what the NIC needs to do is that it has to find multiple paths within the node, okay, to maximize intro and inter-node bandwidth. Okay, this is what it tries to do. Okay, and the model latency and the bandwidth for each algorithm and the protocol based on the number of channels and speeds. So that means the 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 final latency and bandwidth you can get for each algorithm, for each graph search algorithm, the algorithm, the graph search algorithm, the model latency and bandwidth for each graph search algorithm and the protocol based on the number of channels and the speeds. So we can see that because for this one, we can have we have 8 GPUs. We have 8 PCIe adapters, 8 network adapters, and then they are sharing two adapters are sharing one NIC switch. And for this technology, for this one, you can have this bandwidth, which is the total bandwidth can be reached by the multiple graphs, by the multiple rings found out by this graph search algorithm. And for this one, depends on the technology, etc. And this is the bandwidth you can have. And for this one is 48 gigabytes per second, and for this one is 9 gigabytes per second, because here you have only one NIC adapter, so you have the least bandwidth that's normal. Okay, so the step B, which is to build up this to search all the possible graphs to find out all the communication rings that could be deployed for each node topology. Okay, now we need to move to the step C, because right now for step N, A, and step B, we stay within a node. We stay within a node. We build up the topology for node. We have then graph search based on the per node topology, and then, as I said, we have found out so much rings. Okay, so right now you are working with just one node, but the fact is that you want to have multiple nodes to work together to do the computation. Then these nodes, they need to communicate each other. Now we cannot rely on the per node ring or per node graph to do the communication. The per node graph has to be connected to each other to have the global network to carry out this kind of NICO communication. So here we stay with this example, is that you have 4 nodes. For example, you have 4 nodes. The first one, the nearest one, is the node 0, and then you have the second one. Here it is. Here it is. This is node 2, and then you have node 3, here it is, and then you have node 4. The 4 nodes, in the previous example, what we have seen is that you have got a ring. Starting point is the NIC, and end point is the NIC. It passes all the GPUs by using the NVLink between the GPUs, and then it comes back to this NIC. This is a ring. If you can consider this NIC is starting point and the end point. Okay, that's fine. But how should we connect? You are going to have another ring for this NIC, another one for this NIC, and the fourth one for this NIC. But that's for just for one node. How should we connect the nodes together? So how should the node 0 communicate with the node 1? And the node 1 with node 2 and node 3? How they should be connect each other to communicate each other? The simplest way to do that is this one. For the first node, you have an output and input for the first node. You have output, you have input. The output of node 0 will be connected to input of node 3. Okay? And output for node 3 will be connected to input of node 2. Output of node 2 will be connected to input of node 1. Output of node 1 will be connected to input of node 0. Okay, so if you think about this, I mean, it's like a chain. It's like a chain. I mean, here is it's like a chain. It's already a ring per node, and you are going to connect the rings together. The input connects to the output of the other. The input connects to the output and the other, and then you are going to have a big ring. Okay, so you are going to have one big ring for the 4 NICs of the 4 nodes. Okay, and then you are going to have another big ring for the 4 nodes, for the 4 NICs of the 4 nodes. And then again, you are going to have another ring here and another ring here. And then what you have is a big ring. What you have are 4 big rings. Okay, for DGX2 is the same kind of logic. What you are going to have is that this is the first ring, and you are going to have 4 rings in the upper half, and you are going to have another 4 rings in the bottom half. So you are going to have 8 rings. And for this one, you are going to have 4 rings. Okay, you are going to have 4 rings. Okay, so finally, what you have are 4 rings. The GPUs can communicate each other. I mean, you have 4 nodes. The intranode is by going through the InfiniBand. The internode is by going through the PCIe switch, and then the links between the PCIe switch, and then this is the same story for DGX2 systems. But I just want to remind you here, what we are talking about here is logical. It's kind of logical connections. Because what? Because here you have a NIC. You are going to have a adapter here, and except the case that you can separate the input and the outputs, you are going to wear the input and the output by using cables. You are going to have a really physical ring. But in fact, in the real life, is that you are going to have a cable comes from the node 0, and this cable is going to come out here, is going to contain the input and the output. I mean, yeah. And then you are going to have some kind of switch, and you are going to have this cable connected to a port of the switch. Let's see, port 0 is going to be connected here. And the second node, node 1, will be connected by a cable. The cable is going to have both output and input and connected to another port. And then for the third and the fourth, you are going to have cables connected to the switch. This is your switch. For example, we suppose is the InfiniBand switch, and the fact is that the connection are 4 nodes, 4 cables connected to 4 ports of your InfiniBand switch. But in logically, the communication will be the output from the NIC will be going into the switch, and is going to be sent to the through this switch is going to be sent to the last port and goes into the NIC adapter, and then later on, I mean the communication chain will come back and is going to go into this port, and then is going to go here, and then comes back here, and then here, and then here. Now, logically is a communication ring, but physically, what probably you are going to do is that you are going to have just one switch, and you are going to connect all the ports to this switch. That's the same story for this kind of DGX2 systems. Okay, but here is that these 4 NICs are going to communicate each other, and this NIC won't communicate with the others. Okay, it won't communicate with the NIC of this one, of this ring, and it won't communicate with the NIC of this ring. So you have 4 rings, and each ring from the jargon used by Nvidia is a real. So for DGX1, you have 4 big rings, and you have 4 reals, and this is a real. Because the communication is not going from one real to another. So what you need to do if you have to do that, I mean, if you have 4-port switch, which is going to be the best case, you just use the 4 ports of the switch, you connect them 4 ports, you connect to the 4 NICs, and then the communication could be done. You are going to have a logical ring goes into goes in this switch, and goes into this NIC, and goes this NVLink link, etc., etc. Okay, so this is the concept of the real. And we continue. Okay, now inter-node communication, there is the ring we have discussed. And the internode, this is the ring. You have 4 rings, 1, 2, 3, 4 rings, and the latency is ON, is proportional to the number of GPUs you have internode. But there is another way to connect the nodes together. I mean, connect the NICs together. You can say that that's to connect the nodes together, and which is called a tree, which is not a ring, which is a tree. Okay, so you have here a tree. I mean, internode connection is a tree. Internode connection here is still a ring. And internode, if you think the NIC here is a starting point and end point, and you have here still a ring, but between the nodes, what you have here is a tree. Okay? Trees are connected between nodes. Okay, so this is the connection between nodes. Intranodes still aggregate the bandwidth of multiple NICs. Okay? Intranodes still aggregate the bandwidth of multiple NICs. So you have another NIC, you have 4 NICs, you are going to have 4 times the bandwidth of NICs to get out the node. So there's 4 times benefit of NIC to reach out of the server. So this is the the tree topology between nodes, inter nodes. This is the tree topology. Now we need to bear in mind that this is kind of logical tree architecture, because physically what you are going to do, suppose you have a 4-port switch, okay? What you are going to do is that you are going to connect one cable to the fourth, the fourth adapter, the third one, another cable to the third one, and another cable to the second one, and another cable to the first one. This is the first NIC, and then you are going to be done. So physically, what you are going to have, if you have 4-port switch, what you are going to have is that you have 4 cables goes into the 4 NICs, and this is also called a rail. And here we are talking about the trees. Remember, bear in mind that this tree means logical communications between the nodes are trees. I'm going to show you how the trees are. Suppose the internode communication is kind of is using the trees, and then you have 32 nodes. Okay, 32 nodes, suppose you have 32 nodes, and here you have the nodes has been numbered. And basically, if you have a 32 port switch, what I am going to do is that the node 0 will be connected to the NIC 0 of node 0 will be connected to the first port, which is 0, and then where is node 1? The node 1 will be connected to port 1 by a cable, okay? And then the third one will be connected here, and then if you have a 32 port switch, and then the last one will be connected here. Okay, so basically what I are going to get is a switch connected to the 32 nodes. But remember, this is just one rail. What we have seen is just one rail. This is one rail, means that here you are connected to NIC 0 and NIC 0, always NIC 0, and this is rail 0. Remember, there is another rail for rail 1. There is another rail 1 for NIC 1, and there is another rail 2 for NIC 2, and the rail 3 for NIC 3. So at the end, what you are going to have, you have 4 NICs, four rails, rail 0, rail 1, rail 2, rail 3. Okay, now these are the 4 rails. This is the rail 0, rail 1, rail 2, rail 3. Okay. The latency of this communication, internode communication, the latency is proportional to is logarithm to the quantity of nodes. So the latency is smaller because here is proportional to the quantity of nodes because you are doing ring. You are doing ring. You have one more node. You have one more node to pass, so your latency will be increased. But this one, the latency has been reduced, which is proportional to the logarithm of the quantity of nodes. Okay. So NICs still communicate along planes. I mean, here, this is reals. Okay, so this is the internode ring or tree. So up to now, we have gone through step A, B, and C. And right now, we are passing, right now, after we have gone through step A and B and C, which the steps A, B, and C, that, that equals A plus B and plus C, that equals to the nickel initialization functional call. Means that this A, step C, step B plus step C all together are to set up the communication infrastructure that equals to the nickel initialization functional call. Okay, so up to now, the communication infrastructure has been set up. Now the GPUs can communicate each other. Okay, so how the GPUs are going to communicate each other? Okay, the principle here is not complicated. What we need to bear in mind is that step A, step B, and step C, all these steps, the nickel functional call, the initialization of the nickel communication, all the three steps are going to be executed on the CPU, not the GPU, not the GPU, not the GPU. It's not on the GPU, it's going to be on the CPU. Now we pass to the communication part, and this communication part is going to be executed on GPU because this is CUNA kernel, is kind of a kernel functional call. So kernel means that it's going to be executed by the GPU. Okay, so if you still remember that for the intranode communications between the GPUs, we are using NVLink. Okay, so you have a function, you have a kernel core, you have a kernel running on this one, you have another kernel running on this one. Then the root kernels are running on the GPU. Now the kernels, okay, the kernels here, the next GPU, previous GPU, next GPU, the kernels for this kernel is that is going to receive the message from the first in first off buffer of the previous GPU. So this kernel is going to receive the message comes from this first in first out buffer, and this one, and this kernel is going to send the message to this first in first out buffer. First in first out buffer. Okay, and this GPU. Okay, so this GPU is going to receive the message from the previous GPU, and is going to send the message to the next GPU. If we take our all reduce as an example, means what? My GPU myself, I have my data. If we are going to, I have shown you the two short piece of codes which are doing the all reduce of a big array, 32 by 124 by 124. That's a big array. Okay, we need to do the all reduce of this big array. This big array is in the memory of each GPU. You have array in this GPU. You have another array for this GPU. You have another array in the memory of this GPU. So here, if you do all reduce operation, means that this GPU is going to receive the data from this GPU comes from this array, is going to receive the array from this GPU, and then because the all reduce function call in our examples are for sum operation, and that means here the GPU myself, I need to do the sum of the array I have received from the previous GPU, and I'm going to do the sum with the array that I have. I'm going to do the sum, and then I'm going to send the result to the next GPU. And the next GPU is going to do the same thing. So at the end, because if the ring has been passed, all these GPUs has been passed, that means the arrays of all the arrays should have been reduced, and that means each afterward each GPU is going to hold the sum. Is going to hold the all reduce of all these arrays. So this is how it works for the GPUs. So the kernel, what the kernel does is that it runs on the GPU, receives and sends from other peers through internal FIFO first, or buffer, performs reductions and copies with local and remote buffers. Okay, so this is the kernel is doing. Basically, the kernel part is finally that the communication we want to have. Finally, the kernel is doing the communication. Okay. These are the GPUs. The intranode GPUs means that the GPU are interconnect each other by using the NVLink. But here there is another possible scenario. Is that this GPU and this GPU, the previous GPU, my GPU, previous GPU, next GPU, and this is my GPU. I'm the GPU here. And I'm doing the same thing as the previous discussion is that I'm going to receive, let's say, I'm going to receive the array, the three-dimensional array. I'm drawing the cube. This is mentioned three-dimensional array. I'm going to receive this three-dimensional array. Afterwards, I'm going to do the required or reduce operation, So the sum operation with my array. So I'm going to do the sum of these two arrays. I'm going to put the result, for example, here. And then I need to send the result to the next GPU, but the next GPU is not located in the same server. It's located to another server. That means we need to go through the InfiniBand here. The InfiniBand network, I have to go through the InfiniBand network. And then what we need to do is that the InfiniBand need to take the data. Now, this piece of the code, the communication by using the MPI is going to be done by the CPU. This piece of code to send this message, to put this the data here, to take the data and put the data into the adapter, the NIC adapter memory, and put that data into the network, and then deliver the data to the receiver's NIC. All this should be done by the CPU. The CPU is going to execute this part of the code. So it's going to be done by a thread, but it's going to be done a thread, and the thread has to work with host memory, his host memory. So somebody has to copy the data from the GPU memory to the host memory. If you are not using GPU aware, if you are not using GPU aware MPI library. Okay, so this is the difficulty with the GPU communication. Now, at the beginning, I have said that for NICO communication, one thing is complicated because that the communication between the GPUs, the communication infrastructure between the GPUs is going to be set up. Is going to be set up for each launch of the job, and it is going to be one-off. Means after the communication has been done, after the job has been done, the communication infrastructure should has been destroyed. And the next time you need to build up this communication infrastructure again, but that's not the case with this part. This is the InfiniBand. The InfiniBand part, if you have a topology which is a fed tree, means that you deliver the fed tree to the customer, you are going to deliver to the customer, you are going to set up the routing for the customer, fed tree plus the routing, which is for the InfiniBand. So you set up your communication infrastructure for the GPUs. You use this InfiniBand. After the communication has been done, you destroy your GPU communication infrastructure, but you won't destroy this fed tree topology and its routing. You could destroy the per node the topology, the per node graph, and the internode graph connections, etc., which means the step A and B and C we have discussed, but you cannot destroy this routing. So this is for MPI. So MPI is going to be always here. That's the reason why I said at the very beginning that MPI library. To use MPI library, the first thing you need to call is MPI initialization. And this one is less complex than GPU one because here the routing is always there. But for the GPU one, you want to have this GPU to communicate each other, you need to use NICO, and you need to call this NICO initialization, and this one is not the same as MPI initialization because each time you need to go to step A, B, and C is a complex process, and you need to set up your communication infrastructure. Now, after the communication has been done, you are going to destroy this communication infrastructure, but you won't destroy this MPI part. I mean, you cannot destroy the fed tree and the routing of the network for the MPI, the InfiniBand part. So the blue part you won't destroy. The communication infrastructure you have set up for each GPU communication, for each NICO initialization will be destroyed, but not this one. So that's the difference between MPI and the NICO library, and that makes NICO library much more difficult in terms of setting up the communication. It makes NICO much more difficult because it has to deal with three kinds of network: InfiniBand, PCIe, and NVLink. And each time you have to set up it and you have to destroy it. So that's the difficulty with the NICO communication library. Okay. But I also need to point out that, as said by Nvidia in their document, NICO is a complementary communication, collective communication library for MPI. So in the codes, in the part 2 in the code that I have shown you in part 2 and part 3. We have seen that for these NICO communications to work, for this internode communication to work, you have to have this MPI communication at the same time. So you have to mix this MPI plus the NICO to do the communication, and this is the programming model for this GPU computing system with SXM module from Nvidia and OM module from AMD. Basically, the two are the same. So we have gone through these implementation details of the NICO library. I hope I have made it clear. If you have any questions, any comments, you can just send me a message and we can discuss. So for this part, let's stop the recording and we are going to continue after a short break. Bye.